Hello, in this week's video, I want to talk about one of the coolest features of the Go language, and that is interfaces. Now I know that interfaces are normally considered pretty humble features and they sit in the background. It's much more fun to talk about Go routines and channels, especially when you're learning the Go language. But I would argue that the way interfaces are implemented in the Go language are potentially one of the reasons why Go applications tend to be as maintainable and scalable as they have proven to be. So we're going to start this conversation like we start every conversation by introducing the basics. So we'll learn what an interface is and how to use them in the language itself. Then we'll move on to discuss how to compose interfaces together. Now, just like in other high-level languages such as Java or C#, we can actually make interfaces of interfaces. And we'll talk about how to do that and why that's a very good thing to do when you're writing your Go applications. Then we'll talk about type conversion. Now, we've touched on this a little bit before in a previous video, but when we talk about interfaces, things change a little bit, and it's worth revisiting the topic. Along the way, we're going to talk about the empty interface, which is a very useful general construct that we're going to deal with in our programming. We'll also revisit type switches, which we've talked about before, and we'll revisit them in the context of our interface discussion. Then we'll talk about how to implement interfaces, and there's actually two different ways that you can do that. One is by implementing with a value type, and one is by implementing with a pointer. And we'll talk about some of the subtle differences that you're going to run into as you implement interfaces with these two different types. And then finally, we're going to talk about some best practices that have been discovered over the last few years of working with the Go language about how to use interfaces in your actual production applications. Okay, so let's get started by learning the basics of using interfaces in Go. So to start our discussion about interfaces, I'm going to actually build our first application up a piece at a time. Now, often I just drop in code and talk about it, but I want to take this one step at a time so that we're working together and understanding what's going on. So the first thing that we're going to do is we're going to introduce our first interface. So interfaces are a type, just like structs or type aliases. So we're going to start with the type keyword, then we're going to enter the name of our interface, and then the type that we're creating is a type interface. And then we're going to surround the definition of this interface with curly braces, just like we do when we're defining a struct. Now with a struct, we would add in here the data that we want that struct to hold on to, because structs are ultimately data containers, and so that's how we work with them. Interfaces don't describe data, interfaces describe behaviors. So instead of entering a bunch of data types that we're going to be storing inside of our writer interface here, we're actually going to be storing method definitions. So I want to create a write method here, and this is actually an interface from the IO package. We're just going to be working with it here as if we created it. But this is exactly the same interface that you would find in the IO package under the writer interface. So this method is going to accept a slice of bytes, and then it's going to return an integer and an error. Now in the writer interface, the way this works is anything that implements this interface is going to take in that slice of bytes, write it to something. That something might be the console, it might be a TCP connection, it might be the file system. We don't know. We just know that we're writing a slice of bytes to something. And then the integer and error that get returned, of course the error is there in case something goes wrong with the write operation, and the integer is normally the number of bytes written. So now that we have the interface defined, let's go ahead and implement it. So we're going to implement this with a console writer implementation, and that'll be a struct. And that's all we need to do with the struct definition. Now, if you come from another language, you might be looking for an implements keyword or something like that. Well, in Go, we don't actually explicitly implement interfaces. We're going to implicitly implement the interface, and we're going to do that by actually creating a method on our console writer that has the signature of a writer interface. So let me just drop that in, because if I try and type all this out, I will screw it up and then I'll have bugs that I have to go through. So it's much easier just to drop it in. But notice what I've done here. I've got a method on my console writer called write. So it's got the same name as my writer interface. It's accepting a slice of bytes, and it's returning an integer and an error. Now the implementation is whatever I want it to be. Now in this case, all I'm going to do is convert that byte slice into a string and print it out to the console to keep things easy in the playground. But I could have my writer do whatever I want. So what's the value of doing this? Well, the value of doing this is up in my main method, I can actually create a variable that's of type writer, and let me just drop that code in and format it, and set that equal to a console writer instance. So the W variable here is holding a writer, which is something that implements the writer interface. I don't actually know the concrete type though. So when I call the write method down here on line 9, I know how to call that because that's defined by the interface, but I don't actually know in my main function what's being written to. That's the responsibility of the actual implementation. So I could replace this with a TCP writer, I could replace it with a file writer, I could replace it with any other kind of writer, and so I get what's called a polymorphic behavior. Line 9 doesn't care what it's writing to. I specify that behavior before that, but then anything that's going to use this W object just knows that it can write to it, and so it can take advantage of that behavior. So if I go ahead and run this application, you see that I do get Hello Go printed out to the console, just like I would expect. So the key takeaway here, as we're learning the basics of interfaces, is this concept of implicit implementation. So what that means, for example, is if you need to wrap a concrete type and somebody hasn't published an interface, you can actually create an interface that their type implements. So we did it the other way. We created an interface and then we created a concrete type that implemented it, but there's nothing to say we can't go the other way around. We could, for example, go to, if I travel to golang.org and go into packages, this is actually something that I just ran into in order to test SQL database connections. So if I come down to the database package and go into the SQL package, if we look at this, notice that the DB type is a struct. So we don't have an interface here. So if our Go application is talking to a SQL database, we've got concrete types all over the place. So for our transactions, we're interacting with this DB object. Everything that we're doing, sending SQL statements, making queries, are all through this concrete DB object. So how do I test that without a database? Well, the way that you test that without a database is you actually create an interface that replicates this method signature, and the DB object from the SQL package will automatically implement it. So I don't have to worry about creating interfaces at design time if I don't need them for myself, because consumers of my library or whatever I'm creating can always create interfaces later, and their interfaces can be shaped to exactly what they need for their application. Now, another thing that I want to talk about before I move on here is a naming convention. Now, obviously, the name of the interface should represent what that interface is going to be doing for you. And there is one special case. If you've got single method interfaces, which are very common in the Go language, then the convention is to name the interface with the method name plus ER. So if we're defining an interface like we have here with the write method, then the interface name should be writer. If we're going to create an interface with a read method on it, then the interface name should be a reader. Now, if you got more than one method in the interface, things can get a little bit more challenging, but at the end of the day, you should name your interface by what it does, and in the case of a single method interface, just add ER onto the end of the method name. Okay, now in this example, we used a struct, which is probably one of the most common ways to implement interfaces, but you don't need to. Any type that can have a method associated with it can implement an interface. And as we've talked about before, any type can have methods associated with it. So in order to demonstrate that, let me just drop in this example here. Now in lines 16 through 18, I've defined a new interface called incrementer, and that increment is going to be a method that only returns an integer. So it's going to increment something. So whatever we're going to implement this thing with is going to increment values. So down here on line 20, I defined a type alias for an integer called an int counter. And then I've added a method to that custom type on lines 22 through 25, and that's going to be my implementation for the incrementer interface. So the method name is called increment, and it's going to return an integer. Now in this case, look at what I'm doing. I'm actually incrementing the type itself. Since I've got a type alias for an integer, it's a number, so I can go ahead and increment that, and then I'm going to return it as the result of this method call. So I've actually got a type defined on an integer, and the integer itself is storing the data that the method is using. So up here in my main function, I'm going to go ahead and create that integer counter, and I have to cast an integer to an int counter in order to do that. That's what I'm doing here on line 8. And then I create my incrementer and assign that to a pointer of the myInt object, and we'll talk about why that has to be a pointer toward the end of this video. And then I'm just going to loop from 0 to 9, and I'm going to print out the value of the increment method every time I call it. So if I go ahead and run this, I see no big surprise, I get the values 1 through 10 printed out. So what's the takeaway here? Well, you don't have to use structs to implement interfaces. You can use any kind of custom type. Now, I couldn't add a method directly to the int type because the int type isn't under my control. That's defined in another package, and as a matter of fact, that's a primitive type and you can't modify it. But any type that I do have control over that I can create, I can add methods to it, and if I can add methods to it, I can implement interfaces with it. Now the next thing that I want to talk about is how to compose interfaces together, because this is another very powerful concept in the Go language, and is one of the keys to scalability. Because if you remember, I mentioned a little while ago, single method interfaces are very common and very powerful in the language because they define a very specific behavior, but by having a single method, they don't have a lot of opinions, and so they can be implemented in a lot of ways. So for example, the io.writer interface is one of the most common interfaces in the entire Go language because all it does is talk about how to write to things. And we write to things all the time. So by taking as little opinion as possible, we actually make the interface very, very powerful and very, very useful. So let me go ahead and paste this example here, because what happens if we need more than one method, but we can decompose the interfaces down. So in this case, I've created an interface that's composed of other interfaces. So I've got my writer interface that we started the video with, and then I've added this closer interface that just has a close method on it and returns an error, just in case something happened when we tried to call this method. Now the writer closer interface is actually composed of the writer interface and the closer interface. And this is done exactly the same way that you do embedding with structs. We're just embedding interfaces within other interfaces. So the writer closer is going to be implemented if an object has this method on it and this method on it. Then we can treat that as a writer closer. So as an example, I've created this struct here, a buffered writer closer. Now I'm not saying that this is an efficient way of doing things. This is just an example of how you might use this writer closer interface in a way that runs in the playground easily. So in this case, I've got my write method that I'm going to be implementing. And what I decided to do is I'm going to write out whatever gets sent into the buffered writer closer. I'm going to print that out to the console in 8-character increments. So that's what all this code is doing. When you pass data into the write method, it's going to store that in this internal buffer that the struct defines. And then as long as the buffer has more than 8 characters, it's going to go ahead and write that out, but it won't write anything out if it's got less than 8 characters. So we're basically buffering the data that we're sending in. And then down here in the close method, I've got to implement that too. And so what we're going to do there is we're going to flush the rest of the buffer. So I'm pulling the next 8 characters out, and I'm going to write that out to the console and keep doing that until the buffer is empty. Okay, up here in the main method, I simply create a writer closer variable and define that using the new buffered writer closer function. And just to show you that, I didn't talk about it. That's down here at the bottom. That's just a constructor function that's returning a pointer to a buffered writer closer. And I need to do that because I need to initialize this internal buffer to a new buffer. So I have a constructor method there just to make sure that everything's been initialized properly. So if I come back up to the main function and look at that, then I'm going to call the write method. And I'm converting the string, hello YouTube listeners, this is a test, over to a byte slice because that's what the write method expects. And then I'm going to call the close method. So if I go ahead and run this, you see that I get the message printed out to the console in 8-character chunks. And eventually I get all this printed out. But if I comment out this last method call here, you see that I don't get the test part of the string because that's actually a partial. And so we didn't get that full 8 characters that's required for the write method to print it out. And so I didn't actually flush the buffer. Okay, so I know that may be a little bit of a complicated example to show a fairly simple thing, but I just wanted to show you this is how you can compose interfaces together. And as long as you implement all of the methods on the embedded interfaces, then you actually implement the composed interface as well. The next example that I want to talk about is how we can do type conversion. So I'm going to go ahead and replace my main function here with this code here. Get rid of the extra curly brace. Actually, I'm going to get rid of this too. I guess I pulled in the whole function signature. And then I've made a little bit of a change down here on line 13. So lines 9 through 11 are our original implementation, where we're creating the new buffered writer closer, we're writing a string out, and then we're calling the close method on it. But on line 13, I'm actually doing a type conversion. So using this syntax here, where I've got an object, dot, and then in parens, I've got a type that I'm going to try and convert this variable to, and then I can assign that to a variable such as this BWC variable right here. Now, if that succeeds, then everything's fine and I can go ahead and work with it. Now, there's nothing useful I can do with this, but I'm just printing out the variable because I have to use the variables in Go. So I'm just going to go ahead and print that out. So if I run this, I see I get exactly the same output I had before, but now I get the memory address of this buffered writer closer. So that type conversion succeeded, and therefore I can work with this no longer as a writer closer, but as a buffered writer closer. So for example, if I needed to access the buffer directly, then I would be able to do that now, whereas with the writer closer, it's not aware of the internal fields of a specific implementation, and so I wouldn't have access to that data. Now there is a problem, however, if I import the I/O package and try and convert this to a type that it doesn't implement. So for example, if I try and convert this over to an I/O reader, which is another interface, and that I/O reader interface requires a read method on it. So if I try that now, let's go ahead and run that, and we see here we've put the application into a state that it can't manage. And so what it does is what every good Go program does when it can't figure out what to do, it panics. And the panic message is interface conversion. It can't figure out how to cast a buffered writer closer into an I/O reader, and so it's going to fail on us. Now it does give us some useful information about why it couldn't do that. It says it's missing a method read, and then it's going to give us a stack trace letting us know where that error occurred. Now this isn't really great, because sometimes we need to try and convert an interface into something else, and we're not sure if it's going to work or not. So it's not going to be good for our application to be panicking all the time, because then we're going to have recovers, and we're going to be using that as a primary control flow concept, and we want to avoid that in the Go language, because panicking is pretty expensive, so we need another way around it. Well, we just so happen to have another way around it. And so I'm going to show you that. All we need to do, let me rename this variable because BWC doesn't make sense for a reader anymore. I'm going to paste this code in. So I'm going to now try and cast it to a variable called R. I'm going to do the same type conversion, but now I'm using this comma OK syntax. So we've seen this before when we were trying to pull a value out of a map and we weren't sure if it was there or not. Well, we have the same ability with type conversion. If we add a comma OK, this is going to be a Boolean result, and then we can test against that to see if we can work with it. So if the conversion succeeds, then we're going to get an OK value back out. If the conversion fails, then we're going to get the 0 value of whatever type we were trying to convert to. So an I/O reader is an interface, and so its 0 value is going to be nil. So if we go ahead and run this now, we see that our conversion failed, but our application didn't crash. If we switch this back to a pointer to a buffered writer closer, let me go ahead and drop that in, and we run that, we got to drop out our package here that we're no longer using. And then we see that we're back to having things successfully converted, and we could work with that however we needed to. So this is really important to be aware of, especially if you're not sure if you're going to get a pointer or a value type. So for example, it would be really easy to write this and have a problem because we implemented the interface with a pointer, not with the value itself. And so we can't actually do the conversion to the underlying value type. So let's go ahead and run this again. We see that that all works. And one more thing I want to show you. Let me just pull this error back up again. You notice that the reason this type assertion failed is because buffered writer closer does not implement writer closer. Now that might seem a little strange to you because our buffered writer closer has a write method and it has a close method and they have the right signature. So for some reason this works when I ask it to convert it to a pointer, but it doesn't work when I ask it to convert it to the underlying value. Now we'll come back in just a second and talk about why that happens, but I want to finish our discussion of type conversions first. So stay tuned and we'll talk about why that works the way it does. So the next thing that I want to talk about is something called the empty interface. Now the empty interface is exactly that. It's an interface that has no methods on it. And we describe that using this syntax here. Now this isn't a special symbol, this is just an interface that we're defining on the fly and we don't have any methods on it. So it's called the empty interface, but there's nothing special about it. We could create this as the empty interface exactly the same way by just deleting the method out. And that's an empty interface now. So you see it like this all the time. Just be aware, there's nothing special about this. It's just an interface defined on the fly that has no methods on it. Now the nice thing about the empty interface is everything can be cast into an object that has no methods on it, even primitives, because, well, an integer has no methods, and so it can be cast to the empty interface. And so this can be very useful in situations where you've got multiple things that you need to be working with, but they aren't type compatible with one another, and you need to apply some logic later to figure out exactly what you received. But we do have a problem with the empty interface. Because we now have this myObj variable that's defined as an empty interface, we can't actually do anything with it, because myObj has no methods that it exposes because it's an empty interface. So in order to do anything useful with a variable that has the type of an empty interface, you're going to need to do either type conversion, or you're going to need to start using the reflect package in order to figure out what kind of an object you're dealing with. So in this case on line 10, I'm actually trying to typecast into a writer closer, and I'm using the OK syntax to see if that worked. If it does, then I go ahead and call the write and close methods like I saw before. And then I've got this other type conversion that I've done down before just to keep things consistent. So if I run this, we see that I forgot to re-import the IO package. So let me go ahead and pull that back in. And we see that everything works as normal. So the empty interface is very common, but just keep in mind, it's almost always going to be an intermediate step. You're going to define a variable of the type empty interface, and then you're going to have to figure out exactly what you received before you can do anything useful with it. The last thing that I want to talk about in the context of type conversions are type switches. So I want to revisit that conversation from a few videos ago. And just to show you, we can do something like this. So in line 8, I've got a variable I that's defined as the empty interface, and I'm setting it equal to the integer 0. And then I'm going to use this switch block here, and I'm going to use this syntax. So I've got my variable name, I, and then I'm going to use this dot, and inside of parens, I'm going to put type. And so what this is called a type switch. So each of the cases in this type of switch are actually going to be a data type. So in this case, I'm looking to see if I've got an integer or a string, or I've got a default case, which is going to be handled by our application just saying it doesn't know what I is. So if I go ahead and run this, I properly identify I as an integer, so we execute this case here. If I put parens around this, then of course I is now going to contain a string. And so if I run that again, it identifies I as a string. And if I change this once again, maybe we can make this a Boolean. I got to spell true correctly. And I run that, then it has no idea what I is. So this is commonly paired with the empty interface in order to list out the types that you're expecting to receive. And then you would add in the logic of how to process those different types. Now, I promised you that we would come back and talk about that weird type conversion behavior where we could convert our writer closer into a pointer to a buffered writer closer, but we couldn't convert it into the value itself. So now I want to go through and have that conversation about why that happened. So let me just drop this code in. This is a much simpler implementation than what we had before. I've actually not really implemented these methods anymore in order to keep things as clean as possible for you to see. So all I'm doing is I'm going to create a myWriterCloser, and that's down here as a myWriterCloser struct with nil implementations for the methods. But I do have the methods implemented, so I can create this object as a writer closer. And then I'm just printing out the value of the variable just so we have some use for that variable, so the Go runtime will actually compile and run this. And the interface for the writer closer is defined exactly the way we had before. So if I run this, everything works out just fine. However, what happens if I change the receiver of one of these methods to a pointer? Well, if I run this now, I get an error. And the reason that I get that error is it can no longer convert my writer closer into a writer closer interface. And it gives us an interesting message here. It says my writer closer does not implement writer closer. The write method has a pointer receiver. And this is the key to understand what happened with this. So when we define types and we assign methods to them, each one of those types has what's called a method set. Now, when you're working with the types directly, the method set is all of the methods, regardless of the receiver types, associated with that type. With interfaces, however, things change a little bit. When I implement an interface with the concrete value, so notice here I'm creating a myWriterCloser. I'm not taking the address of a myWriterCloser. I'm using myWriterCloser directly. So WC is defined as holding the value myWriterCloser. So the method set for a value, when we're talking in the context of an interface, is any method that has a value as the receiver. So the reason we're not implementing writer closer is because a write method no longer has a value receiver, it's got a pointer receiver. And so its method set is incomplete. Now we could fix this by using the address of operator and running again, and notice now everything works. And the reason for that is the method set for a pointer is the sum of all of the value receiver methods and all of the pointer receiver methods. So let's go through that again. When I'm implementing an interface, if I use a value type, the methods that implement the interface have to all have value receivers. If I'm implementing the interface with a pointer, then I just have to have the methods there, regardless of the receiver type. So the method set for a value type is the set of all methods that have value receivers, but the method set for a pointer type is all of the methods with value receivers as well as all of the methods with pointer receivers. So there's a couple of ways that we could fix this. Now in this case, we don't need access to the underlying data, so we could just go back to a value receiver, and then this is going to work just fine. This is actually the initial example we had. If we have one method that's got a pointer receiver, however, we're going to need to switch that over to a pointer type. And notice I can actually remove this, and it continues to work, or I can make both of these pointer receivers, and this continues to work as well. So this is an important concept when you're implementing your own interfaces. If any of the methods require a pointer receiver, you're going to have to implement that interface with a pointer. If not, though, if all of the methods accept value types, then you can go ahead and use a value type if that's what you want, but you could also use a pointer. Okay, the last thing that I want to talk about are some best practices when using interfaces in your own Go applications. So let's take a look at those. Okay, when we're working with interfaces, there's a couple of rules and guidelines that I'd like you to keep in mind. And these have been developed over the last few years by the Go community and are generally accepted as some of the best ways to use interfaces if it's practical in your applications. The first is prefer many small interfaces versus large monolithic ones. Now, if you need large monolithic ones, that's fine. Go ahead and compose smaller interfaces together to make those. But the smaller you can make your interfaces, the more useful and powerful they're going to be. And that's not actually unique to Go. No matter what language you're working in, if interfaces are there, generally having many smaller interfaces is preferable in the long run to having a few monolithic ones. Now, some examples that are in the Go standard library are the io.writer interface, the io.reader interface, and the empty interface. Now, these are arguably three of the most powerful interfaces in the entire language. And if you think about it, writer has one method, reader has one method, and the empty interface has 0 methods. So it's interesting support to the argument that smaller interfaces are better, that some of the most powerful interfaces in the language contain 1 or 0 methods on them. Now, when you're working with interfaces, if you're coming from a language that has explicitly implemented interfaces, you're going to be very tempted to create interfaces and export those. So here's the guidance for that. If you don't need to export the interface yourself, so if you don't have any particular reason to do it, go ahead and don't. So there are some good examples of why you would want to do that, but often it's perfectly acceptable to export the concrete type. I'll take as an example the database/SQL package that we looked at earlier in the video, where we saw that the DB object was exported as a concrete struct, and it had all sorts of methods that pointed to other concrete structs. So you can't directly mock that out for testing right out of the box. However, by not exporting an interface, it allows you as the consumer of that struct to define your own interface that you can use for testing. And the beauty of that is, if you don't use every method on the DB object, your interface doesn't have to have every method on it. You can just expose the methods that you need. However, do export interfaces for types that you will be using. So if you're going to pull a value in, go ahead and accept an interface instead of a concrete type if at all possible. So this is going to be almost exactly backwards from how other languages consider interfaces, and the reason is that whole idea about implicitly implementing interfaces instead of explicitly doing it. So if you were working in Java or C#, you could not do this, because you have to define the interface before you implement the interface, because they're explicitly implemented. But since Go has implicit implementation, you can go ahead and defer the creation of the interfaces until exactly when you need them. So if you're creating a library that other people are going to consume, you can define the interfaces that you accept, and then they can provide whatever implementations that they want. Now, if your library has reasonable defaults, then you could export those concrete types as well, but make sure that you're accepting interfaces whenever possible. And that's what this third point is talking about. Design your functions and methods to receive interfaces whenever possible. Now, that's not always possible. If you need access to the underlying data fields, then certainly take in the concrete types. But if you're accepting behavior providers, then go ahead and try and accept those as interface types instead of the concrete types. Okay, so that covers what I want to talk about with interfaces today. Let's go into a summary and review what we've talked about. In this video, we've talked about interfaces and how to use them in the Go language. We started with a discussion of the basics of interfaces, so how to create them and how to implement them. And we ended up with code that looks something like this. So we're defining an interface as a type. So we're going to start with the type keyword, the name of the interface, and then the keyword interface. And then inside of curly braces, things are going to be a little bit different than if we were defining a struct, for example. If we were defining a struct, we would put data fields inside of the curly braces because we're defining the data that that structure is holding. With interfaces, we're defining behaviors, however. So instead of adding data fields, we're going to add method signatures. So we see here in this example, we're going to define a write method that accepts a slice of bytes and returns an integer and an error. And then we implement that interface by creating a method on our type that has the same signature. So we don't have to explicitly state that we're implementing the interface. We implement the interface by implementing the interface, by having the methods there that match the type signature for the interface's method. Then we talked about how to compose interfaces together, and how this is a preferable approach versus creating a single monolithic interface. If you can, break that interface down into smaller types and then compose them together. And we did that something like this. So we're going to create multiple interfaces. So we have a writer interface and a closer interface. And then when we compose them together, just like when we compose structs by embedding, we can embed interfaces into one another. So we can create a writer-closer interface that embeds the writer interface and the closer interface. So to implement that writer-closer interface, you have to implement the write method because that's defined by the writer interface, and you have to implement the close method as it's defined by the closer interface. So by doing this, you can actually pass smaller chunks of your interface around your application. So for example, if a method only needs a writer, it doesn't need a closer, then you can actually pass this writer-closer as a writer, and it'll work just fine, versus passing the entire writer-closer along and potentially exposing methods to the consumer that aren't really necessary. Then we talked about type conversion and how we can drill through the interface to get at the underlying types in case we need to work with those directly. So we had an example here where we created a writer-closer instance, and the underlying type was a pointer to a buffered writer-closer, and how we could cast that back to a pointer to a buffered writer-closer by using this syntax here, where we have a dot after the object, and then inside of parens we put the type that we want to cast to. Now, we learned that when we did this, if the type assertion failed, then we're actually going to panic our application. So remember to use that comma OK syntax if you want to get a Boolean variable out that you can run tests against to see if that type conversion succeeded. And then we talked about the empty interface and type switches. The empty interface is nothing magic. It's just an interface defined on the fly that has no methods on it. Now, it's special in that every type in Go implements the empty interface. So you can store anything you want in a variable of type empty interface. And then very often we're going to pair that with what's called a type switch. And we see an example of that here, where we're going to use the switch keyword, we're going to have the object, and then dot and parens like we do with a type assertion, but instead of having a concrete type that we're asserting against, we put the keyword type in there. And then in our case statements, we're actually going to put in the data type that we're asserting against. So in this case, we're looking for integers or strings, or we have a default case in case the value stored in I is neither an integer nor a string. After that, we talked about implementing with values versus pointers, and we learned about a concept called method sets. Now, when you're working with types directly, you never have to think about this because the methods are always all of the methods assigned to that type. But with interfaces, the rules change a little bit. The method set of a value is all of the methods with value receivers. So if you're going to try and implement an interface with a value type, then all of the methods that implement that interface have to have value receivers. With pointers, things are a little bit more flexible because pointers always have access to the underlying type as well. The method sets for a pointer is all of the methods regardless of the receiver type. So all of the value receivers as well as all of the pointer receivers. So pointer types are definitely more flexible when you're implementing interfaces. Just keep in mind, you don't want to assign pointer receivers everywhere without thinking about the idea that that gives access to the underlying data of that type, and so that can allow methods to alter that underlying data even if you don't want them to. So be careful when you make that choice about using pointer receivers or value receivers. The last thing that we talked about were some best practices that have evolved over the last few years about using interfaces in the Go language. And we talked about use many smaller interfaces whenever possible, and then if you need larger interfaces, go ahead and compose those together with interface composition. Don't export interfaces for types that will be consumed. So if you're creating a library and somebody else is going to be consuming a type, go ahead and publish that concrete type out there. Don't create an interface assuming you know how people are going to use it. Allow them to create the interfaces that your type will implement. That way they don't have to implement a whole bunch of methods in their test suite that they never even use. Do export interfaces for types that you will be consuming, however. So again, these 2 points are exactly opposite of how you're going to think about interfaces if you're coming from another language such as C# or Java that have explicit implementation of interfaces. So when you're defining a type that you're going to be consuming in your package, then go ahead and export interfaces. That way whoever's using your package can create their own concrete types and implement the interfaces that you need, so you don't need to worry about the implementation. You just need to worry about the behaviors that they're exposing to you. And then, if possible, define your functions and methods to receive interfaces. Don't get too crazy with this, so don't go over the top. Use common sense with this. But if you have the option of receiving interfaces, for example, if you don't need access to the underlying data, then go ahead and define an interface that you're going to be receiving. That way, it makes your methods and functions more flexible, since you can have multiple implementations that you never thought about at design time, and your functions and methods will continue to work even when those new concepts are thrown at your application. Okay, so that wraps up our discussion of interfaces. I hope you've learned a lot. I actually learned quite a bit when preparing for this video. If you have any questions or comments, as always, feel free to leave those down below, and we'll come back at you soon with a new video introducing the Go language.